Hi, this is going to be a walkthrough for the OChem 1 Workshop 2 worksheet for Autumn 2025. So the first question goes through hybridization, how to identify the hybridization for each highlighted atom below. And so briefly, what exactly is hybridization, why it's important? In short, it just allows for the best geometry to space out those electrons, which don't really like to be around other electrons. If you recall, it's because if you have two like charges, they will exhibit those electrostatic repulsions. And if we have that in a molecule, it's not really going to be fun for the molecule, right? It's going to create instability rather than stability. So let's take a look at this simple ketone right there. If I just pointed out um, this carbon exhibits an sp2 hybridization as well as this oxygen. And so with that sp2 hybridization, they exhibit a trigonal planar geometry. And so that this is also special so that this carbon and this oxygen's p orbitals line up, creating that pi bond right there. So it's not also to allow the best geometry to space out those electrons, but it also explains how bonds are organized in a molecule. Anyway, so let's go through the first problem in this worksheet. And this one is actually ricinin, right? So in the worksheet, it asks us to look at the hybridization of this carbon, this nitrogen, and also this nitrogen here. Let's start off with this carbon. Right off the bat, I will tell you one simple trick that I like to use, and that is just taking, let's see if you can write, the number of things attached minus 1, right? I don't know if you can see that. I hope you can see that. And so what I mean by number of things attached, I mean by direct attachment. Let's look at this carbon. It's directly bonded to one thing as well as another thing. We're not counting the bonds, we're only counting the number of things attached to it. And so 1, 2, minus 1 becomes sp1, or just sp. And then if we look at that nitrogen there, in the nitrile, the triple bonded functional group, then we can see that it's bonded directly to one carbon, and it also has one lone pair of electrons. And so I would count the lone pair of electrons minus 1, it also becomes sp. Okay? Looking at this nitrogen here, if I wanted to talk about the hybridization, then I would count 1, 2, 3, 4, counting the electrons, lone pair, minus 1, that's sp3. However, one thing is very special about amides. If I draw the structure here, we notice that because this carbon here has a partial positive, this oxygen has a partial negative. Partial negative because oxygens are electronegative, they want more electrons, right? Or they can handle more electrons. This nitrogen wants to donate into this C to N bond to create more stability in that molecule or that amide. Right there, right? This is just resonance talk, right? This nitrogen can donate and do more resonance to become more stable. Because of that, if we look at this structure right here, this nitrogen exhibits a 1, 2, and usually it has a hydrogen 3. If we have that, then 3 minus 1 is sp2. So in reality, this nitrogen here in the amide is sp2 because of that resonance. So let's look at sp2. And if I wanted to talk about what kind of orbitals overlap to create a bond, then I would just say that this nitrogen, creates a bond with this carbon. This is also sp2. And so the orbitals that overlap to create this sigma bond is the overlap of the carbon sp2 and the nitrogen sp2. Let's talk about why that is, or how can we actually visualize that. most simply, let's talk about this nitrile. And to do that, to visualize what kind of orbitals are overlapping, you're going to hate me for this, but we have to reach back into our Gen Chem lines and talk about electron configurations and orbital diagrams. It's very simple, don't worry, I will try to simplify it. But let's take carbon. What is its electron configuration? This electron configuration is 1s2, 2s2, and 2p2. The 1, 2, 2 here, or like the coefficients, are just telling you the levels, the ground level or whatever. The SSP is just talking about what kind of orbitals. And the exponents here just tell you the number of electrons in those orbitals. Let's do it here. Actually, no, that should be wrong. So if I lay out my orbital diagram, 1s, 2s, and 2p, then put in my electrons, represented by these half arrows. 2 electrons here. I want to space out my electrons because, once again, electrons don't really like to be near other electrons. So that's why I space them out. It's like being a roommate, or having a roommate. Why have to share a room with a roommate if you don't need to, right? And so, since I'm expecting this carbon to be sp, then that just means that I'm going to combine my 2s orbital shell with one of my 2p hybridize. And so now I have 2 sp orbitals, and the rest of these unhybridized orbitals are higher in energy and are just p orbitals. And so we organize our electrons like so, represented by half arrows again. 1, 2, 3, 4. And looking at this carbon, it has 1 and 2 sigma bonds, represented by these. So 1 electron goes to make a bond with this carbon right there. The other electron goes to make a sigma bond with this nitrogen there. Now what about these 2p orbitals? Well, these 2p orbitals are going to be used to make that overlap needed for those pi bonds right there. Remember that p orbital electrons are being used to make pi bonds. What about this nitrogen? Very fast. Nitrogen is pretty much very close to carbon on the periodic table, or it's just one atom, or well, one placement away. So the electron configuration here is 1s2, 2s2, 2p3. Okay? Now we just make our orbital diagram, 1s, 2s, and then 2p. Make our electrons, and then 1, 2, 3. We're also expected to make an sp orbital out of this nitrogen, so we're just going to mix our 2s orbital with a 2p, hybridize, then make 2 sp orbitals once again, and another 2 p orbitals. Now I have 5 electrons, 1, 2, 3, 4, 5. And right off the bat, we can see that this nitrogen has a lone pair, and that's notated by this full sp shell. Nitrogen makes one single bond, dictated by this sp orbital with 1 electron, and 2 pi bonds, because it has 2 p orbitals that it can make, to make those 2 pi bonds. God damn. Anyway, and just as a quick reminder, when I have 2 atoms that want to bond, let's say 1, 2, 3, 4, 1, 2, 3, 4, a bond consists of how many electrons? Just 2. Just 2. So this carbon has 4 electrons, this carbon has 4 valence electrons. You may not be able to see it right there. That's better. Okay. So these 2 carbons have 2 electrons. They can make a bond. Like so. All right. So And I'm not going to be doing every single question in this worksheet because that will take so long for me. And I only get paid for so long, so. Let's talk about penicillin G and its hybridization. There. Okay. So penicillin G looks like this, with a benzyl group here, attached to an amide. And something very interesting, a four-membered cyclic ring. And carboxylic acid. Okay, so this is penicillin G. And we want to describe the hybridization of both nitrogen amides. I'm not going to do the electron configurations like for ricin, but right off the bat, like the amide in the last example, these two are sp2s. Because if we remember, nitrogen can do resonance and exhibit sp2 character. Typically we would say like 1, 2, 3, 4 things are bonded or attached to that nitrogen, minus 1 is sp3, but because it has that resonance, it exhibits sp2 character. And then the next question is to talk about the stability of these two amides, the one that's outside of the ring and the one that's cyclic. And so something that we notice is that sp2 let me backtrack. So pretty clearly we see this pretty strained four-membered ring, right? And we can kind of tell that it has 90-degree angles, 90-degree bond angles. If we just look at this one carbon, make sure to label your hydrogens right there, then if we do our little trick, 1, 2, 3, 4 minus 1 is sp3, this carbon is sp3, same one as this carbon. And so what kind of bond angles do sp3 hybridized atoms like to make? So I have already made one, but let's look at this. sp3s, like this molecule here, typically don't really make that 90-degree angle, but instead something more of a 120-degree bond angle. And so the fact that this ring contains that sp3 hybridized carbon, as well as the other ones, but exhibit a 90-degree angle, tells me that this is pretty unstable, right? And so it goes for this nitrogen. This nitrogen does have a lone pair it can donate because it is part of an amide, right? So what if I were to do resonance? What if I were to do resonance and make this double bond between the carbon and nitrogen in the ring? Well, we have to remember that double bonds are typically shorter than single bonds, right? And so having this length being reduced because of that pi bond makes this more unstable. This four-membered ring more unstable because, once again, we are being forced into this 90-degree angle when we want to have a 120-degree angle. And this pi bond here will make this more unstable because we want to be more spread out, right? We want to be more stable, more length, right? Okay. At least when we're talking about strained ring structures. And so really, to answer that question, what is the stability of the beta-lactam nitrogen, this one, versus that acyclic nitrogen, the one outside of the ring, is that the nitrogen, or the amide, outside of the ring is much more stable because it's not constricted by ring strain or bond angle strain. And the nitrogen in the beta-lactam ring is less stable because of that much more extreme bond angle strain from that little box ring. So, does resonance really occur in this beta-lactam part of that molecule? It can, but partially it doesn't actually delocalize fully, because if we did indeed do that resonance, then it would just make it more unstable. Okay. And this kind of ties back into the next question, where it talks about 1,3-cyclobutadiene. So what does that look like? Here. Okay. So 1,3-cyclobutadiene is literally just this, right? It has a square, four-membered ring with 2 pi bonds. And you might be wondering, like, can it do resonance? Just do that? Can it do resonance? Well, that's what these questions are going to walk us through for, right? So the first thing it asks us on the worksheet is to define or identify the hybridization of each carbon in this molecule. So if we just draw that here, this carbon has 1 hydrogen attached. So 1, 2, 3 minus 1 is sp2. This carbon is sp2, right? And we can, since it's just a box, we can also assume or note that all the other carbons are sp2, right? So since it's sp2, what kind of molecular geometry should that carbon have? Well, remember the example that I showed you before with this ketone. The carbon and the oxygen here should be in the same plane, right? They should be in the same plane because they're both sp2. sp2 atoms typically exhibit a trigonal planar geometry, right? That's why we have this, right? Right, trigonal planar geometry. But does this really have trigonal planar geometry? Well, let's look. So I built here kind of a cyclobutadiene. It's not really a square, but it's more of a rectangle because these pi bonds, these double bonds that you can see right there, are a little bit shorter than the ones single bonds here. So we would see a 90-degree bond angle with this molecule, but these carbons, you kind of see the bend in these single bonds. They don't really want to be at a 90-degree angle. They want to be at a much more stable 120-degree, or 120-degree bond angle, since they're sp2, not 90-degree. That's horrible, right? And so, because they're forced to be that way with the 90-degree bond angle, it's very, very distorted. The geometry is very distorted, and so it cannot keep up a typical planar geometry. Instead, you can kind of see here that it's a little puckered. It's a little puckered, right? Maybe you can't see, but I don't know. You can kind of see. Let's see. You can kind of see that it's a little puckered and it's a little distorted. But because of that distortion, it can't really keep up that trigonal planar geometry. And so the last question asks, does resonance, displayed right here, does that really occur? The answer is no, because resonance is based on the geometry and the hybridization. If the hybridization is sp2, that's great. But if the molecule doesn't exhibit that trigonal planar geometry that it needs, then no, resonance will not occur. That just goes to show. No, very bad. So the next question, 3, talks about how is the 1,3-cyclobutadiene different than benzene. I'm not going to explain that, but you can build off of my explanation for 2 to answer 3. All right. So let's go over resonance, the last thing on the worksheet, as well as the one thing that starting OChem students kind of have trouble with. Resonance. what exactly does resonance do, or what does that really allow for us? Well, for the molecules, resonance helps for those delocalization of electrons. And when I mean delocalization, I'm talking about the movement of electrons so that the electrons are shared between molecular areas, right? So for resonance in molecules, it allows for that delocalization, or the spread or shared of electrons, shared movement of electrons. And for us as chemists or as students, it allows us to see the reactivity of those atoms or areas in the molecule due to the movement of electrons. So let me write that down. So it just allows us for snapshots of reactivity in a molecule. And so the biggest pattern of resonance that I want you to walk out with after this video, big pattern. Please identify this in every molecule that you see. What is the big pattern that I'm talking about when I'm looking at resonance? Since we're looking at the movement of electrons, where do the electrons go? They go from electron rich to electron poor. That is the biggest pattern that you should look for when you're doing resonance structures, right? So, what are these electron rich and electron poor sites that I'm talking about? Well, if we talk about the sources, then we can talk about, well, electron-rich places, most obvious, of course, are places that have extra electrons, or like anions, or like carbocations, C-, right? Areas that have electron-poor areas are cations, or carbocations, right? They have extra electrons so that they can donate to the anions, to cations. This also goes for, lone pairs, things that have lone pairs. And lone pairs can also donate to cations. But what's also not obvious is partial charges. We talked about that ketone, that C double bond O. C double bond O. Remember that oxygen is electronegative, right? Because it's right next to fluorine on the periodic table. So the dipole goes up. Oxygen is greedy. The oxygen wants more electrons. It's very hungry for electrons, right? So this becomes partial negative. And what do you guess? This carbon is partial positive, right? So areas that are electron poor, partially positive atoms. Areas that are electron rich, positive, partially negative atoms. And another source of electron rich areas are pi bonds. And when I'm talking about pi bonds, I'm talking about double bonds, triple bonds, never single bonds. You can never break a single bond, absolutely not. If you do, I will hunt you down. Absolutely not. So let's observe the first molecule in this worksheet, talking about resonance. And I have a simple cyclopentadiene with a anion right here. And so we just talked about it. Electron-rich carb anions are good sources of electrons, right? And while we may not see an electron poor site, we can definitely make one. So carbon doesn't really like having a charge, let alone a negative charge, so it really wants to get rid of it, right? So this electron, these pair of electrons are going to be donated to make a ring, not a ring, a pi bond between this carbon and that carbon. But, oh no, this carbon has 2, 4, 6, 8 electrons. We can't make this pi bond, so this has to go somewhere. So this pi bond will break and become part of this carbon. So notice that I did not break this pi bond, nor did I exceed the octet here, nor did I break a sigma bond, a single bond, right? Also note that I have the same formal charge in both of these structures. Now can I do the same thing here? Of course, this carbon doesn't really want a negative charge, so it makes a pi bond there. And then same thing again, this carbon already has its octet, 2, 4, 6, 8, because in covalent bonds, it's like we're sharing electrons, so I can become an octet, right? So this carbon has 2, 4, 6, 8 electrons. If I did make a pi bond there, then this would exceed the octet rule. So then I would have to make a move for these electrons upwards to that carbon. Notice that I didn't break that pi bond that I just moved in the first one. Notice that I didn't break a single bond. Notice that I didn't exceed the octet, and if I was going to, then I would have to push electrons elsewhere. And also note that the formal charge is still the same, -1, -1, -1, right? And we could go around the ring all over, until we end up at the same place, right? But, that would take forever. We would bracket. Here we go. So why can I do this? Why can't I put a lone pair on a carbon? Well, carbons may have an empty p orbital where it can hold the extra lone pair. Does it really want that? Not really, but it definitely can hold a lone pair, right? Carbons don't want lone pairs, they want to get rid of it. So having this network where this carbon can dump electrons elsewhere to not have a lone pair, it shares a weight. It shares the weight of not wanting something, which is the electrons, right? It's like hot potato, if you think about it. So let's look at the second example. Second example, wait, what? Oh, I just did the second example. Let's do the first example, excuse me. Again, a cyclopentadiene with a plus charge, okay? So we just talked about electron poor areas. We have a carbocation, lacking electrons, let's count. Carbocations mean that it has 3 valence electrons instead of 4. So it has 1, 2, 3. 3 valence electrons making it a positive charge. So where can I get 4? My answer is in those electron-rich areas, in these pi bonds, right? I can move either pi bond, really. It doesn't really matter because it's symmetrical. I can move it and fulfill this octet. This carbon used to have a positive charge, now it doesn't. But where does the positive charge go? Well, we can see that this carbon and that carbon had to share a bond to have 8 electrons in total. Then this carbon decides, hey, I want to make a bond with this carbon instead because it's unhappy. So that kind of just leaves it with a plus charge. Then we do the same thing here, move these pi bonds to this pi bond, single bond, making a double bond makes that carbon happy. So really, if you just think about it, it is hot potato. We could do this all over again until we end up same place. Okay. Notice that I didn't break a single bond. I also have the same charge on each structure, and I'm not breaking the octet rule. Okay. Let's go over one last example because my voice is getting tired. Let's talk about this one. Okay, so right off the bat, we can see that we have a pi bond, and a carbanion. So we have a lot of electron-rich areas. Do we see any electron poor areas? Do we? Well, your hint is around this oxygen. This oxygen is what? Electronegative. So it'll pull electron density towards it. Dipole again to show that. And so this oxygen, while it may not have that negative charge, still has that partial negative charge. This carbon has a partial positive charge because electron density is being sucked away from it. Right? So, seeing that, we can see that we can indeed do resonance. We can go from electron rich to electron poor. So why don't we do that? Electron rich. But oh no, that, moving those electrons, is going to break the octet here at this carbon. Why do I need to move this pi bond? Because electrostatic repulsions. Electrons don't want to be near other electrons. So, by abiding by that, as well as not wanting to break the octet rule, we move this pi bond upwards to the oxygen, and we make a new resonance structure, where this oxygen has that full negative charge. This pi bond moves, satisfying this carbon, but we need to place a positive charge because, let's see, this carbon had one hydrogen, so 2, 4, 6, 8. What about this carbon that was having this pi bond? This carbon has one hydrogen, 1, 2, 3 bonds, meaning it needs a positive charge. Don't forget that we have a negative or carbanion, and then again, electron rich to electron poor, making this structure right here. Let's see. Okay. If you also wanted to, you could just move this electron, this lone pair. So we only have that and a full plus charge there, while keeping the rest of the functionality in the molecule. And then we can also see that the net charge in each structure is the same. They didn't break any single bonds. Electron rich to electron poor. There you have it. That is resonance for that structure. Okay. I hope that helped at least some bit. Resonance is pretty hard to do as a OChem student if you're just looking at it. But if you realize that there are actual patterns to look at when doing resonance, then you can definitely take a jab at drawing resonance structures. It really is just moving electron rich to electron poor. But also just recognizing that maybe you may not see electron-rich areas or electron-poor areas, but you can certainly make some innately there in the molecule, right? And one other thing, you really do need to look at the book. I'm not trying to mom you, but it really is very beneficial for you to practice, because as you have seen me do throughout this video is draw structures on the board. I'm always drawing something, right? Organic chemistry is very tactile. And so if you don't really do that practice or just get on the board and just start drawing things, you don't really develop that feel, you know? Organic chemistry, yes, it does require logic, but it also requires you to develop that sense of intuition, which is why practicing builds that intuition, that feel when you draw things, you know? I've done this so many times that I can really just tell you straight off the bat that, oh, that's electronegative, electropositive, so you can do resonance, right? So the more you practice, the more you will build that intuition and the faster you will get through these things, right? Anyway, good luck. I'm rooting for you. Have fun. Bye-bye.